Hi, it's Professor Adam. Let's have another look at large molecules, this time using the projection operator method on boron trifluoride. From our previous video, you may remember that we started solving molecular orbital problems using a 6-step process involving determining point groups, assigning axes, finding reducible and irreducible representations of group orbitals, which were then combined with the central atom atomic orbitals of the same symmetry to obtain the full molecular orbital diagram. Now we are going to consider a non-trivial example, with boron trifluoride Bf3 being a good example because it is planar and has more than 2 atoms in its group orbitals. For the most part, our procedure follows the same pattern as before. First, we assign the point group. Bf3 is planar with the D3H point group. The axes then need to be assigned. The principal axis of rotation will be the z-axis. The y-axis will point along the molecular bonds, and the x perpendicular to it, meaning that each of the outer atoms has a different set of coordinates. With these Cartesian coordinates, the 4 fluorine valence orbitals will adopt these configurations. Next, we want to find the reducible representations for each kind of atomic orbital, each of the s and p orbitals. We can convince ourselves of these reducible representations because, for example, the 2 s orbitals are 3 for E, under C3 rotation all move giving 0, for C2 rotation 1 remains static giving a value of 1, under sigma H nothing moves giving a character of 3, under S3 all of them move, and a vertical mirror plane passes through one atom and not the others. Then we reduce these reducible representations using our equation to give the irreducible representation shown here. In principle, we have a 6x6 character table, so we would have to go through all 6 and assign how many of these are in each of the reducible representations. It turns out that for the 2s we have A1' and E', and so on for the other orbitals. We now have assigned the symmetry for all of our group orbitals. Now we need to know how to put them in our color diagram. What do they actually look like? Our orbitals all have E character, which means a 2x2 matrix, meaning it has expressions in 2 axes for the E'. This means that we expect one of the orbitals in the E' set to be x-like and the other to be y-like. This also means the 2s reducible representation contains 3 orbitals, 1 from the A1' and 2 from the E' irreducible representations. Looking at the 2s orbitals then, let's try and construct their diagrams. The A1' is just the totally symmetric representation and has all the s orbitals in phase. But what do the E'X and E'Y look like? As we have 3 orbitals, we need a procedure to make sure we obtain the correct combination for our linear combination of atomic orbitals. This is the projection operator method, which will give us a systematic way to find our symmetry-adapted linear combinations from the atomic orbitals. The projection operator method will only give us one of the E' orbitals. The other we obtain from normalization and orthogonality. We label our fluorine 2s orbitals A, B, and C and do the symmetry operations on fluorine A, which gives us this table. We are considering the Fa atomic orbital. Under the identity, nothing happens and Fa is still Fa. With a C3 rotation, we do anti-clockwise rotation and Fa becomes Fb, and under another rotation, it becomes Fc. For a C2 rotation along the A axis, nothing changes and the Fa is still Fa. Under a C2 along the B axis, Fa becomes Fc, and so on for all of the other symmetry operations. The group orbital wave functions can be determined by multiplying the projection table values by the character of each irreducible representation and summing the results. So, for the A1' representation, we multiply Fa by 1, and then Fb by 1, and so on to the end, giving us the sum total as this, which can then be simplified so that A1' is equal to 4Fa plus 4Fb plus 4Fc, or that there is equal contribution from each of the orbitals Fa, Fb, and Fc. Thus, A1' looks like this. We can then go down the character table and do the same calculation for each representation, such as A2', and we will obtain this function that when we collect the terms will cancel out and give A2' is equal to 0, which means that there is no function that can be formed using these three orbitals. But we already knew that as we determined that the irreducible representations of the 2s orbitals were A1' and E'. The last one that we will consider is the E' representation that we know is present, and we get this function with lots of zeros, which when we collect terms, E' is equal to 4 times Fa minus 2 times Fb minus 2 times Fc. This means that Fa should be double the size of Fb or Fc, and because of the minus sign, Fb and Fc have an opposite phase to Fa. Before we had this slide and we wanted to know how we could get values for E'y. Well, now we know what E'y looks like, we can get E'x by normalization and orthogonality, where the square of the wave function integrated over all space is equal to 1. The first thing to do is to normalize the wave functions. We will start with the A1' and E' wave functions that we have and then use those results to find the third wave function. The first wave function is the A1' and is an equal mixture of the 2s orbitals. We need to find Ca in order to normalize the wave function. We then square the wave function over all space, making this equal to 1, while moving the Ca term outside as it is just a number. Expanding this out would give 9 terms, however the only 3 non-zero are the overlap of the fluorine orbitals with themselves. The others are too far apart and their integral will be 0. This then gives these 3 terms as the only ones that are not 0. The integrals of the square on Fa, Fb, and Fc. Then we have the condition that Ca squared times 1 plus 1 plus 1 is equal to 1. The normalization condition, because these atomic orbitals are all equal to 1, as the atomic orbitals are individually normalized, unlike molecular orbitals. We can then solve this for Ca, which is Ca squared is equal to 1 over root 3. We then insert this into the original equation to get the normalized A1' molecular wave function. Next, we look at the E'y. In the molecular orbital wave function, the contribution of Fa is twice that of Fb or Fc, and Fb and Fc have a different phase from Fa. The coefficient is then determined using the normalization requirement, and again we only have 3 terms because the only overlaps are between the atomic orbitals and themselves. Then we have a sum of 3 terms with each atomic orbital integral being equal to 1, which gives us that Ca squared times 4 plus 1 plus 1 is equal to 1, which can be simplified to give Ca is equal to 1 over the square root of 6. Which then gives us the normalized molecular wave function for E'y. This information, and especially the coefficients for A1' and E'y, can be used to determine what the third molecular wave function will be. The coefficient squared gives us a probability of finding an electron in an atomic orbital within a group orbital, and it is important to realize that the sum of the squares of the coefficients is equal to 1. So for A1' we have 1 over root 3 squared is a third. There are 3 orbitals, meaning a third plus a third plus a third gives 1. As the 2s orbital of Fa lies on the y-axis, it will be predominantly used for the E'y interaction and having 0 contribution with the E'x group orbital because of the node defined by the yz plane. This means that only Fb and Fc can contribute to E'x, and their contributions can be determined by cataloging the squares of the coefficients for the normalized equations shown in this table, as the sum of the coefficient squares must be 1 to ensure equal contribution from each orbital. Thus, for Fb and Fc we have coefficients of either plus or minus 1 over root 2, with the negative sign on one of them because of the node in the yz plane and to ensure x-like character. This means that the orbital we are looking for must have this wave function with no contribution from atom A and atoms B and C having opposite phase. Now we have the final piece of our puzzle to determine the two s fluorine group orbitals, as E'X has equal but opposite contribution from Fb and Fc with zero contribution from Fa. The orbitals on Fb and Fc are bigger than those in the A1' and E'Y orbitals. It has x-axis character as it has a node in the middle and runs from negative to positive. The projection operator method can also be used to generate the group orbitals of Px, Py, and Pz, and the results will be very similar to what we got for the 2s, so we can use that and our knowledge of the 2s orbitals to help us form the 2p orbitals as well. These are the 12 group orbitals from the set of fluorine valence orbitals. The 2p orbitals follow the same pattern as the 2s orbitals. This can be done through the rigorous method we used for the 2s orbitals. The symmetry of the central boron atomic orbitals needs to be known so that the energy and symmetry appropriate molecular orbitals can be formed. There are 2 group orbitals and 1 atomic orbital with A1' symmetry, 8 orbitals with E' symmetry, 2 atomic orbitals, and 6 group orbitals. Finally, we have 2 orbitals with A2 double prime symmetry, 1 each from boron and the group orbitals. This leaves us with 3 group orbitals without symmetry-matched pairs, which will be non-bonding. Looking at the E' orbitals, the E' of the 2px orbitals have very little overlap with the boron atomic orbitals and will not interact well, resulting in these orbitals becoming essentially non-bonding. Now that we have determined the orbitals that can be combined based on symmetry, the orbital energies must also be considered. The fluorine 2s orbital is too low in energy and will be non-bonding, but the other orbitals of fluorine and boron are energetically close and can be used to form the molecular orbitals. Now we can construct the molecular orbital diagram for Bf3 with boron on the left and the group orbitals on the right. The orbitals from the 2s of the fluorines are non-bonding because they are too low in energy to interact with the valence orbitals of boron. As usual, we start with the sigma orbitals and then the pi orbitals from top to bottom. Here we have sigma interaction between the 2 A1', which is clearly a sigma type interaction, making a bonding and anti-bonding combination where the s mixes with the A1' group orbital set, which is the totally symmetric set. Then we have interaction between E' giving 2 sigma bonding and 2 sigma anti-bonding, which are both degenerate. Remember, E orbitals always have a degeneracy of 2. This then leaves us with only one orbital, the A2 double prime, from the Pz. The A2 double prime gives a pi-type interaction with bonding and anti-bonding orbitals. This then accounts for all the bonding and anti-bonding interactions in this system. This leaves the remaining orbitals as non-bonding orbitals, 3 totally non-bonding due to symmetry, and 2 mostly non-bonding from the poor overlap of the 2px E'. In total, there are 24 valence electrons, 3 from boron and the rest from the fluorines, which we will fill into the molecular orbitals like so, from lowest to highest, with the highest occupied molecular orbital being non-bonding. So the HOMO is non-bonding and the LUMO is a pi star molecular orbital. Let's check comprehension.